Welcome back to ECE 320A. We're now in Unit 6, and in Unit 6 what we are doing is continuing with our Laplace transform material, and in particular inverse Laplace transforms. And now we want to push it one step further and deal with repeated roots, whether those roots are real or complex. Now we want to know what actually happens when we have roots that are sitting on top of each other. And that's what we want to work with today, is try to identify the pattern or the structure in the time domain expression associated with repeated roots. You have homework number 6 that will be due at the end of Unit 6, and exam number 3, as a reminder, will be coming up after Unit number 8. One thing to maybe just keep in mind when we're doing inverse Laplace transforms and we have repeated roots, again, that means that in the denominator we might have something like s plus a cubed. We now have 3 roots at minus a. That's what we mean by repeated. There is the distinct root when we just have s plus a, but if we now have that factor squared or cubed or raised to a higher power, that's what we're meaning by repeated roots. And when we have repeated roots, one thing that you can maybe think of is our time domain expression needs to be, our time domain expressions for the different parts of that repeated root need to be independent. And one way to maybe keep that in mind is to stick a t in front of the expression. That's what I'm going to maybe continue to suggest that you keep in your head when you have a repeated root, is stick a t in front of it, and we'll see what that means or what that indicates in the next line. Here is an example. Suppose we have a transform, capital F of s. Now we have 2 poles on top of each other, 2 roots of our denominator at s equal to minus p1. Those are the values of s that cause that denominator to vanish. We have another root of our denominator at s equal to minus p sub 3. That one is actually distinct. But when we are doing our partial fraction expansion, when we have repeated roots, we have to actually accommodate all of those different possibilities, meaning we not only have to have an a sub 2 over the s plus p1 factor, but we also need to have another partial fraction expansion term, a sub 1 over s plus p1 quantity squared. If we had another pole or root of the denominator at p sub minus p sub 1, where the factor s plus p sub 1 was cubed, then we would need an s plus p sub 1 cubed term. We would need an s plus p sub 1 squared in the denominator of a second term, and we would need a third term with an s plus p sub 1. So in the partial fraction expansion, we start with the highest power of that pole, and then we just keep adding factors until we're down to a simple factor associated with that repeated pole. Once we have that, then the structure that is associated with that can immediately be inferred from that partial fraction expansion structure. And in particular, we should be able to very quickly see that over on the far right with the a sub 3, that's a distinct pole, and that has associated with it the classic a sub 3 e to the minus p sub 3t time domain expression. A sub 2 looks very similar in terms of its partial fraction expansion term, and in fact it is. It's now a sub 2 e to the minus p1t. But when we have this square or repeated root in the denominator, then we need the time domain expressions associated with those 2 partial fraction expansion terms to be independent which is now why I'm saying stick a t in front of it. Now we have a sub 1t e to the minus p1t. If we had a factor s plus p1 actually cubed, not only would we have these two terms associated with the p1 pole, but we would also have a third term that would be, let me say, a sub 4 a sub 4 t squared e to the minus p1t. And that will just keep continuing as long as we have higher and higher powers or repeats on that particular pole. As you can infer from this partial fraction expansion structure, the a sub 3 can be found in the way that we've been doing it in previous units or in previous material. We can use the distinct root approach, and in the next lecture or video we will actually talk about other ways of finding this, but we've been talking about the cover-up method, which is a pretty clean way and efficient way to try to find these partial fraction expansion coefficients, a sub 3 and a sub 2 in this case. We can't find a sub 1 that way. I'm sorry, we can't find a sub 2 that way. We can find a sub 1, and we'll say that in just a minute. But a sub 3 can be found using the cover-up method, which means that we multiply through by the polynomial expression underneath a sub 3 on the left-hand side. That cancels, and that's where this cover-up comes from. We're essentially covering up this s plus p sub 3 factor in the f of s equation or expression, and then we evaluate that result at s equal to minus p sub 3 in order to find that residue a sub 3. The case 1 cover-up method, case 1, remember, is for distinct roots. That can also be used for the highest or the coefficient associated with the highest power of the root. In this example, the coefficient associated with the highest power of the root is a sub 1. So we can find a sub 1 using our classical cover-up method if we want to. We can multiply through by that denominator factor underneath a sub 1, which is s plus p1 squared, multiplying that times the transform, capital F of s. That s plus p1 squared cancels the s plus p1 squared in the denominator, and so we don't have any issues with something vanishing or blowing up when we're solving for a sub 1. A sub 1 will just be the evaluated number that comes out of calculating or putting in s equal to minus p1 in that expression, n sub 2 of s over s plus p sub 3. We can't, though, use that cover-up method to find a sub 2. If we multiplied through by the factor underneath a sub 2, we would still have an s plus p1 downstairs on the left-hand side and underneath a1, and those two, when we evaluate those at s equal to minus p1, would go unbounded, and that doesn't provide us with an opportunity to find this unknown coefficient a sub 2. The cover-up method doesn't work, but there are many techniques that can be used, and we'll talk about those in the next video. But for now, let's just talk about the structure that we will see when we're trying to find a sub 2. So we'll just leave it at many techniques for finding a sub 2, and we'll talk about that in the next video. When we're finding a sub 2, however, we are going to assume that we've already found a sub 1 and a sub 3 using these previous approaches. So now the only unknown in this partial fraction expansion structure is this unknown coefficient a sub 2. That's the only remaining unknown. And here is what you can start to associate with these repeated roots. Let's look at the case when they are real roots. Up above, we just found that when we had a double pole at some value, in this case it's a, then we stick a t in front of the time domain. If we didn't have that s plus a quantity squared, we would simply have an e to the minus at. But since we're squaring it, then that particular time domain expression needs to be linearly independent from e to the minus at, and we can achieve that by actually sticking a t in front of the earlier e to the minus at. If that's the case, then what would you expect the structure to be associated with 1 over s plus a cubed? Now the pole at s equal to minus a is there 3 different times. What would you expect the time domain structure to be? Well, in general, we would say, well, we had t e to the minus at u of t, but we need to stick a t in front of it. So that's what we're going to do. And in fact, as we add more and more poles, we also have to introduce a little bit of a change in the coefficient that scales that expression. But now the inverse Laplace transform of 1 over the quantity s plus a cubed will be 1 over 2 factorial. That exclamation point is meaning the factorial, where 0 factorial is 1, 1 factorial is 1, 2 factorial is 2 times 1, etc. So we now have 1/2 t squared e to the minus at u of t. And we can continue with that. And in general, if we start with 1 over s plus a raised to the n plus 1 power, now we don't have any scaling, the numerator is just 1, then we have 1 over n factorial. This is 1 less than the power of the root. The pole is now repeated n plus 1 times. We take 1 over 1 less than that, factorial, so we have 1 over n factorial, t to the n. Again, that's now 1 power less than the repeated roots, e to the minus at, and we want that to be on for time t greater than or equal to 0. So that's the general formula. You will find that structure in the book. It looks a little bit different, but I hope you can see the connection. Here, they go ahead and assume there's a coefficient, a non-unity coefficient in the numerator. Let's say it's k. And in the denominator, we have a factor that's repeated r, as in rabbit, times. Then to take that into the time domain, we would scale it the same, so k is there, but now we divide by r minus 1 factorial. T, we have how many t's? Well, we have r minus 1 t's in front of it, and we have the exponential because of the pole at s equal to minus a. So we have k over r minus 1 factorial, t to the r minus 1. Those are 1 fewer in number or quantity than the number of roots at that location with the exponential e to the minus at. If we had complex roots, then it's really not that much different, but it does look a little bit more involved. That's because now we have complex poles. Let me go ahead and indicate where those would be. Let's say now we have a minus alpha and a j beta. If we have a pole there, which of these 2 partial fraction expansion pieces correspond to that particular pole? One corresponds to that pole, and another one corresponds to this pole, its conjugate down below. But we are interested in writing this expression such that k here is associated with this particular pole, and this particular pole is associated with that factor, because if you now look at solving that factor or setting that factor equal to 0, you will see that S is equal to minus A plus J beta. That's the root of that factor, and that root is in the second quadrant. And that is very important in terms of that's the one that we actually associate with this K and not the conjugate. Now, if K ends up having a negative angle, that's fine. Its conjugate, K star, would then have the opposite sign for its angle. But now, once we found K, then we can inverse Laplace transform that using the formula on the right, which is 2 times the magnitude of that complex number K. Remember, K is a complex number. We're then writing it in polar form, or K now has a magnitude and an angle that we're calling theta. Then the time domain expression will be 2 times the modulus or the magnitude of K, t to the r minus 1. This r minus 1 again is 1 less than the repeated or the total number of roots at that location. E to the minus alpha t, cosine of beta t. Beta again is coming from the imaginary component of the root. Alpha is coming from the real part, that's the amount of damping. And theta, this particular theta, is associated with whatever angle is here, that needs to be there. If theta is negative, that negative goes in that location in the cosine argument. And again, we're doing the one-sided Laplace transform, so that is valid for t greater than or equal to 0. The key piece, or one of the key pieces, is you need to associate the k that is above the s plus alpha minus j beta factor with the pole in the second quadrant. That's the k, not the k conjugate. K conjugate is associated with the complex conjugate of the pole, which this one is now at s equal to minus alpha minus j beta. That's what you need to keep track of in terms of the structure of the time domain expression associated with repeated poles.